Hello everyone, my name is Hirofumi Fukuyama. First of all, I'd like to thank the DEAIC 2020 Conference Committee members, particularly to Professor Sang-Muk Lim and Professor Jiu Zhu for inviting me as keynote speaker. The title of my presentation is Capacity Utilization and its Empirical Extensions. Capacity utilization is a well-known concept which represents the extent to which a firm, industry, region, or country uses its installed productive capacity. Capacity utilization can be shown as the ratio of observed output that is produced with the installed equipment and the maximum potential output which could be produced with it if the capacity were fully utilized. The capacity utilization concept and the observed output are clear, but the definition of capacity is less clear. As a consequence, two notions of capacity are given in the capacity utilization literature. One, economic concept of capacity, and two, physical or engineering concept of capacity. These concepts are of great importance because the implications from the two concepts can provide different policy suggestions. The first concept of economic capacity requires information on prices, but the second concept of physical capacity does not. Although the first concept is of sufficient importance, the requirement of price information hinders the use of this concept in many practical situations. In contrast, the second concept only requires information on input and output quantities, and hence it is easy to implement. Regarding studies on firms, industries, regions, and countries, many recent empirical studies have indicated large inefficiency levels, in particular when these entities are modeled as multi-output producers. As a consequence, the efficiency measurement approach has become a standard empirical tool for serving a variety of managerial policy and regulatory purposes. There is a huge literature applying the efficiency measurement approach for examining economic entity performance-related issues. To just name a few, the efficiencies of real estate companies, banks, regions, and healthcare systems have been examined. However, many studies on efficiency measurement literature do not explicitly consider capacity utilization in their analytical frameworks. The focus of this presentation is to study capacity utilization within the framework which allows for technical inefficiency. Therefore, integrating capacity utilization and efficiency measurement is of great significance in order to provide accurate policy or managerial suggestions. Motivated by the limited numbers of significant empirical investigations based on the physical notion of capacity utilization for the situations where inefficiency is allowed. Here, we focus on the popular efficiency measurement approach called data envelopment analysis, or DEA. which can implement capacity utilization rather in a simple way. The organization of this presentation is as follows. First, I will provide some basics on the notion of capacity utilization. Second, I will explain one of my recent papers related to DEA-based capacity utilization in some detail. Finally, I will show some capacity utilization structures which are adopted in some of my other papers. Let me start with the basics on the concept of capacity utilization. In recent years, a number of researchers in the business economics, operations research, and management science literature have looked at the issue of capacity measurement. As mentioned earlier, these studies may be roughly divided into two categories. One, those that uses price information, and two, those that consider only physical or quantity information in deriving capacity utilization indexes, measures, and indicators. Coeli et al. 2002, for example, discussed each of these categories as 1. Economic definitions of capacity, which is related to price information. 2. Physical definition of capacity, which is related to quantity information. The first one is analyzed based upon price information using value functions such as cost, revenue, and profit functions. Among the three functions, the cost function is the most frequently used tool to study the economic definition of capacity measurement. For the estimation of the cost function, information on input prices is needed in addition to output information. The second one utilizes Johansson's physical concept called plant capacity utilization, which states the maximum amount that can be produced per unit of time with existing plant and equipment, provided that the availability of variable factors of production is not restricted. Quite often, it is difficult to obtain price information, in which situation Johansson's approach is appealing because it requires data only on physical input and output quantities. Hence, when information on prices is unavailable or unreliable, Johansson's idea of plant capacity utilization becomes a nice alternative to the economics definition of capacity measurement. In view of this, Fair, Groskopf, and Kokelenberg, 1989, developed a data envelopment analysis-based capacity utilization measure following Johansson's plant capacity utilization concept. After the operationalization of plant capacity utilization suggested by Fair et al. 1989, many researchers have adopted the capacity utilization notion in DEA setting. Johansson defined capacity output as the maximum output that could be produced when at least one input is fixed but without limits on variable inputs. Weiergroskop and Kokelenberg derived a measure of capacity utilization using DEA. Huxley, Morrison, Paul, and Squires 2002 overviewed the conceptual basis for the measurement of capacity and the capacity utilization. In a multi-output setting, Fair and Groskop of 2000 proposed a ratio-form directional capacity utilization measure based on an unknown-oriented directional distance function. Coeli et al. 2002 measured capacity utilization as the gap between observed short-run profit and the maximum short-run profit. Saho and Tone 2009 developed quantity-based measures of capacity utilization and decomposed overall efficiency into technical efficiency, rate economic capacity utilization, and optimal capacity idleness. For a recent survey on the basic models, see Cesaroni et al. 2017. Consider single output production possibility set denoted by uppercase letter T. Suppose f of x is a single output production function where x displayed in bold type is a vector of input. We further assume that the bold font x consists of two kinds of inputs, fixed input x superscript f and variable input x superscript v. Johansson's capacity utilization concept is basically the output-oriented one. Hence, the production function defined as the maximum output given input is used. Alternatively, the radial output distance function can be used. The radial output distance function is very useful to deal with multiple outputs. The restricted radial output distance function, d of bold font x and the non-bold font single y, is defined as the reciprocal of maximum expansion of the output quantity by holding all inputs fixed. The radial output distance function d is represented by Shepard 1953 and 1970 and indicates radial output technical efficiency. To model capacity utilization efficiency, we need to use two types of production functions or radial output distance functions. With respect to the radial output distance function setting, we employ the restricted radial output distance function d and unrestricted radial output distance function d hat, with the hat on the top of the uppercase letter D. By analogy, we can denote the short-run versions of production function and the radial output distance function for a fixed input x super f. But note that this short-run radial output distance function allows the variable input to be scaled by variable delta hat. The unrestricted radial output distance function d hat is denoted as the reciprocal of maximum expansion of the output quantity given the fixed input. The effect of this definition is that the variable input is treated as if it is not in the production vector. Therefore, the restricted radial output distance function takes a value no less than the unrestricted radial output distance function. The efficiency decomposition is presented by directly using the definition of capacity utilization efficiency. That is, unrestricted radial output efficiency is multiplicatively decomposed into capacity utilization efficiency and restricted radial output efficiency. This decomposition can be used to examine the sources of unrestricted radial technical inefficiency. Unrestricted radial output efficiency, which is the left-hand side of the decomposition, can be thought of as overall capacity technical efficiency. As an example of empirical extension of capacity utilization framework, this presentation examined the environmental and energy efficiency or prefectural efficiency of 47 prefectures in Japan for fiscal year 2001 to fiscal year 2014 based upon the capacity utilization framework with a two-stage network production structure. The first stage is obtained as the intersection of two sub-technologies. For the construction of the first sub-technology of stage 1, a prefecture is assumed to convert two variable inputs, labor and energy, and one quasi-fixed input, public infrastructure, to produce energy-related undesirable final output of CO2 emissions, as well as an intermediate good output, gross value production. In the second sub-technology of stage 1, polluting byproduct is generated by the specific inputs of energy. Here, the labor variable input is assumed to be a variable unlimitedly, but the energy variable input is to be reduced. Regarding stage 2, the prefecture produces well-being outcomes using the intermediate product from stage 1 as an intermediate input. The structure of the current presentation of Japanese prefectural efficiency is given as in the slide. I start with the methodology consisting of conceptual framework and the modeling framework. Next, I talk about the data. Here, constructions of inputs and the output are discussed. Then I move on to provide empirical estimates and some policy implications. The final part concludes with the summary. Our two-stage network production model is shown in Figure 1. In Stage 1, The DMU uses physical capital K, labor L, and energy E to produce an undesirable output of CO2 emissions, denoted B, and intermediate product Z. Here, Z is the gross value of production. Physical capital K is a quasi-fixed input, L is unlimitedly available variable input, and E is a variable input to be reduced. L can be increased or decreased. So L and E are differently modeled here. Public infrastructure is a proxy of physical capital K. Note that energy is directly related to production of CO2 emissions B. Stage 2 uses Z to produce a final desirable output Y. As depicted in Figure 1, the intermediate product Z is assumed to be the only input to stage 2. In this study, public infrastructure is the quasi-fixed input. The reasons for treating public infrastructure as the quasi-fixed input are: 1. Public infrastructure cannot be instantaneously adjusted to current production. 2. The short-run quasi-fixity of public infrastructure causes its rigidity, and hence the adjustments require over several time periods. These characteristics of short-run quasi-fixed public infrastructure can well be implemented in a DEA-based capacity utilization framework. The variable samples are given here in the slide. Stage 1 sub-technology 1 is the technology producing good output. Hence, it is the standard technological representation. By contrast, Stage 1 sub-technology 2 is the technology related to emission generation. Consider the material balance condition Murty-Russell and Levkov 2012 and Murty-Russell forthcoming implement what they call costly disposability between the emission causing input and the generation of the emission. The costly disposability property leads to a positive relationship between the emission causing input and the emission along the frontier. In our case, energy E is directly related to the production of bad output B. Combining stage 1's two sub-technologies, intermediate product Z is produced. Stage 2 uses Z to produce a final desirable output Y. As depicted, intermediate product Z is the only input to stage 2. The overall network production possibility set is obtained by combining stage 1 and stage 2 technologies. Mathematically, the uh, overall network production possibility set is expressed as the one at the bottom. Here, we summarize stage 1 technology, which is constructed by the intersection of the two sub-technologies. The production variables K, L, E, B, Z, and Y are in the overall network technology T. The two sub-technologies are given in the middle. The important feature of these sub-technologies is that the energy input appears in the constraint of both sub-technologies. Combining the sub-technologies as the intersection, we obtain stage 1 technology. We adapt the emission-generating mechanism proposed by Murty-Russell and Levkov 2012. That is, stage 1 technology is obtained as the intersection of stage 1 sub-technology and stage 1 sub-technology 2. According to Finn-Forson, joint production is best formulated with multiple sub-technologies in an overall production possibility set. This slide shows how costly disposability and standard strong disposability differ. If the bad were a good output, then the pink area would be the relevant production possibility set. But the bad is not a good output, so it should be modeled differently. We model such a technology by adopting the costly disposability assumption. This assumption leads to the blue area where inefficiency is allowed on the part of management or decision-making entity. This slide shows the pollution-generating technology or by-production technology proposed by Multi, Russell, and Levkov, 2012. Pollution is treated as an output in Murty et al.'s pollution-generating technology that satisfies the assumption of costly disposability and violates the standard disposability property. The costly disposability property is denoted at the top of the figure. It states as follows. Suppose that all production variables K, L, E, B, Z, and Y are in the production possibilities set, and E prime is no greater than E, and E prime is no less than B, then the production vector KL E prime B prime Z Y must be in the production possibility set. The biproduction technology is an intersection of the intended production technology and nature's pollution generating technology. Note that this idea is given in Murty et al., but the term costly disposability is formally introduced by the forthcoming book by Murty and Russell. The idea of costly disposability is considered to be a joint disposability concept. Ray and Mukherjee implemented joint disposability between the polluting output and its pollution-causing input based on weak disposability between them. This slide shows the DEA-based technology and the two directional distance functions to construct the capacity utilization indicator of inefficiency. A restricted directional distance function serves as a functional representation of the technology T. This function takes the form as presented in the first definition in the slide. Given fiscal capital and labor, the restricted directional distance function seeks the maximum contraction in energy and emissions and simultaneous expansion in the desirable output for the respective directions. We also estimate an unrestricted directional distance function that allows the producer to adjust labor to capacity. The unrestricted directional distance function is denoted by beta O hat star in the slide. Since the labor can be scaled by the factor delta L hat, the technology set expands if the DMU is not at capacity. This slide gives the interpretation of capacity utilization and two directional distance functions, beta O star and beta O hat star. When beta O star is equal to 0, the DMUO to be assessed produces on the frontier of production possibility set D. When beta O star is greater than 0, the assessed DMU is inefficient, with higher values indicating greater inefficiency. By construction, we have beta O hat star is greater than or equal to beta O star. And beta O hat star is equal to 0 indicates that DMU 0, the DMUO produces at capacity. We define capacity utilization efficiency for DMUO as the difference between beta O hat star and beta O star. It is appropriate here to clarify the standard, radial, and directional approaches. This slide summarizes the notation and definitions on the standard radial approach and our directional approach for the clarification purpose. The important difference may be stated as follows. The standard radial approach provides a multiplicative efficiency decomposition. By contrast, the directional approach provides an additive inefficiency decomposition. Moreover, radial approach considers efficiency, but the directional approach estimates inefficiency. This difference arises depending upon whether a researcher adopts the radial or directional approach. The last two expressions show some similarity to the relationship between ferrule efficiency and directional inefficiency decompositions. After the oil embargo of 1973, Japan passed the Act on the Rational Use of Energy in 1979. This act was expected to reduce green gas emissions via energy conservation prior to the Kyoto Protocol of 1992. Under the Kyoto Protocol, Japan committed to emissions cuts of 6% from its 1990 levels by 2008 to 2012. However, Japanese government officials are recently encountered opposition to energy cuts as citizens have become more aware of its costs. Moreover, in the wake of Fukushima Daiichi nuclear disaster caused by the Great East Japan earthquake on March 11, 2011, improved energy efficiency and reduced energy demand have taken on added importance as it is nuclear it, it is unclear whether alternative sustainable energy sources will be sufficient to offset the lost nuclear energy. Real gross domestic product of gross value of production is often used to measure aggregate well-being, but other important social indicators related to health and environmental quality are considered by the United Nations Human Settlements Program in 2012. Instead of using the prefecture's contribution to the gross value of production as the final output, we use it as an intermediate product that is used to produce the final desirable output. The final desirable output is an aggregate index of 10 economic and social indicators tracked by the Organization for Economic Cooperation and Development, or OECD, that is constructed using the benefit of the doubt method. The Better Life Index was developed by the OECD and ranks countries based on 11 dimensions shown in Figure 5. These dimensions include current material conditions, quality of life for the current generation, and the expected well-being of future generations. We dropped the subjective well-being dimension of the Better Life Index and construct our composite indicator of final output from the remaining 10 dimensions of the Better Life Index using the better benefit of the doubt method. The benefit of the doubt method gives each prefecture the benefit of the doubt regarding which of the indicators the prefecture deems most important. This figure shows an alternative pictorial representation on the consumption of our integrated composite well-being indicator representing good output. As stated before, we dropped the subjective well-being dimension of the Better Life Index and construct our composite indicator of final output from the remaining 10 dimensions of the Better Life Index. In addition to income and earnings, the OECD also tracks quality of life as measured by environmental quality and health status that are thought to contribute to sustainable well-being. The benefit of the doubt method uses linear programming to aggregate multiple sub-indices into a composite indicator. Here, we use the super-efficiency modeling method to improve discriminatory power. To estimate the restricted and unrestricted directional distance functions, we used prefecture-specific directions. Thus, the directional distance functions beta O star and beta O hat star measure the simultaneous proportional contraction in bad output and energy and the proportional expansion in good output that could be achieved via greater technical efficiency and improved capacity utilization. We have two definitions related to capacity utilization. Definition 1, the prefecture O is said to have absolute excess capacity if capacity utilization inefficiency is greater than 0 and the scaling factor delta LO hat is greater than unity. When the scaling factor delta LO hat associated with the labor input L is greater than unity, the implication is that DMUO requires the increase in the labor input and the full capacity for the for full capacity utilization. Definition 1 adapts Kirkley Morrison Paul and the Squires 2002, Young and Fukuyama 2018, and the Fukuyama, Liu, Song, and Yang 2020. The other definition is definition 2. The prefixure O is said to have labor-specific excess capacity if capacity utilization inefficiency is greater than 0 and the scaling factor delta LO hat is less than unity. When the labor variable input is less than unity, it implies that the observed quantity of the concerned input exceeds what is needed for full capacity utilization. If the absolute excess capacity prevails, then the policies that leads to reduction of the fixed input will be desired. However, for the case of labor-specific excess capacity, policy suggestions can be made such that input substitution is promoted. Now turn to the inefficiency estimates. Table 2 shows as follows. The pooled inefficiency average is 0.1535 for the restricted directional distance function. The pooled average inefficiency is 0.15500 for the unrestricted directional distance function. Capacity utilization inefficiency averaged is 0.0015 and 556 prefectural observations had capacity utilization inefficiency indicator is equal to 0. The first equation shows how to obtain the target labor input associated with the capacity output. The solution to the unrestricted directional distance function beta O hat star can be supported by multiple values for the scaling factor delta L. Therefore, we estimated the minimum value for the scaling variable and the maximum value for the scaling variable that are consistent with the given value of unrestricted directional inefficiency beta O hat star. Noting that the delta hat max is greater than or equal to delta hat min, we classify DMU as follows. DMU has a labor shortage if and only if delta hat min is greater than 1. DMU has a labor surplus if and only if delta hat max is less than 1. Labor is used efficiently if delta hat max is greater than or equal to 1 and delta hat min is less than or equal to 1. Regarding the way of estimating delta hat max and delta hat min, please see the article by Fukuyama, Hashimoto, and Weber 2020. Annual counts of prefectures with a shortage of labor, a surplus of labor, or that are labor efficient are reported in Table 3. We have classified the DMUs based on the method shown in the previous slide. Given physical capital, 28% of the prefectures had the shortage of labor, 15% of prefectures had the surplus of labor, and the remainder operated at capacity. Relative to capacity employment, the average prefecture had a surplus of 34,000 workers, which is about 2.6% of average employment. Labor shortages existed only in 2007 and 2014. As reported in Table 4, 123 prefectures had positive capacity utilization inefficiency. Between 3 and 4 prefectures had positive capacity utilization inefficiency during 2001 to 2004. 21 to 22 prefectures had positive capacity utilization inefficiency during 2005 to 2008. In the year 2008, population reached its peak. Only 0 to 1 prefectures had capacity utilization inefficiency during 2008 to 2013, when population started to fall. In 2014, 22 prefectures had excess capacity inefficiency. Thus, the peak in population coincided with excess capacity in infrastructural capital, but that misallocation rapidly disappeared from 2008 to 2013. For the 123 prefectures with positive capacity utilization inefficiency, the average capacity utilization inefficiency was 0.01. That is, in addition to the gains to be had from greater technical efficiency, the gains from operating at capacity could have simultaneously reduced energy and bed output by 1% and increased good output by 1%. Roughly 19% of the prefectural observations had excess capacity. The prefectures with excess capacity averaged 6.86 million yen in physical capital per capita, relative to the 6.18 million yen in the prefectures that operated at capacity. During 2001 to 2005 and 2009, the intermediate product G was lower in prefectures with excess capacity relative to prefectures that operated at capacity. The prefectures with positive capacity utilization inefficiency also had smaller populations, approximately 1.52 million people, relative to 2.96 million people in prefectures with zero capacity utilization inefficiency. The trends in inefficiency are depicted in Figure 6, with the average restricted directional inefficiency and average unrestricted directional inefficiency measured on the left axis and the capacity utilization inefficiency on the right axis. Unrestricted directional inefficiency trended down from 25% in 2001 to 10% in 2010 increased to 20% in 2012 and fell to 12% in 2014. The average restricted directional inefficiency had a similar trend. The measured unrestricted directional inefficiency means that composite well-being could be increased by greater technical efficiency in the use of energy. Furthermore, the decline in energy use would also allow CO2 emissions to decline. In contrast, capacity utilization efficiency averaged less than 0.5%. Capacity utilization inefficiency moved sideways from 2001 to 2004. From 2004 to 2006, capacity utilization efficiency increased, which coincided with Koizumi administration's fiscal and administrative reforms on local governments. After the reforms were fully implemented and adapted to, average capacity utilization inefficiency decreased during 2006 to 2009 and fell to zero during 2010 to 2013. According to the Porter hypothesis, stating properly designed environmental standards can trigger innovation that may partially or more than fully offset the costs of complying with them. This hypothesis can be applied to prefectures as if they are regulated industries with the central government as the regulator. During the first commitment period, 2008 to 2012 of Kyoto Protocol, Japan agreed to reduce emissions by 6% below its 1990 levels. From 2001 to 2007, the prefectures with excess capacity were unable to reduce emissions due to greater capacity utilization. But from 2008 to 2013, most prefectures made effective adjustments to capacity, which helped reduce energy use and emissions. Capacity utilization efficiency increased from 2013 to 2014 as 22 prefectures had excess capacity compared to only one prefecture with excess capacity from 2008 to 2013. This deterioration in capacity utilization might have occurred due to the Great East Japan earthquake on March 11 in 2011. To build public infrastructure, and the central government increased taxes but gave less consideration to how the funds would be allocated. The massive investments made in the damaged areas might have caused this lagged effect on capacity utilization and efficiency. We developed a capacity utilization DEA framework to investigate the prefectural or environmental and energy efficiency of Japanese 47 prefectures during fiscal year 2001 to fiscal year 2014. According to the United Nations World Commission on Environment and Development, chaired by Guro Harlem Brundtland, 1987, sustainability is the development that meets the needs of the present without compromising the ability of future generations to meet their own needs. Since the Commission's initiative, the three aspects of economic and social and environmental development have recently been at the center of sustainability issues, which are closely related to people's well-being and human development. Therefore, we have treated well-being as the final output of a prefecture. Our capacity utilization model finds that the 28% of the prefectures have surplus labor amounting to 34,000 workers, which are about 2.6% of the workforce. In per capita terms, the prefectures with excess capacity tend to spend more on public infrastructure capital and generate less income per person than prefectures that produced at capacity. Before finishing my presentation, let me explain some of my papers adopting the concept of capacity utilization. The below are my papers dealing with capacity utilization. Five papers are as follows. This Omega paper studies efficiencies of Chinese provinces. The employed inputs and outputs are assets, labor, energy consumption, capital stock, GDP, CO2 emissions, and CO2 NO2 emissions. This paper utilizes fixed inputs, variable inputs, desirable outputs, and undesirable outputs, in addition to the linkage between certain inputs and the outputs based upon the weak disposability property. The objective in developing the capacity utilization indicator is to measure the extent to which the current variable inputs of the assessed DMUs are utilized to produce the maximal amounts of good outputs. In the empirical study, we use a dataset of 30 Chinese provinces. In the second paper published in Socio-Economic Planning Sciences, we studied the Chinese manufacturing industries. The variable inputs are labor and energy. The assets are a quasi-fixed input. The desirable output is industrial production. The bad output is the CO2 emissions. This paper deals with mutual fund management. The aim of this paper is to determine whether observed outputs justify the observed level of disbursements. Disbursements include three of the nine stage-level inputs considered as factors of performance. Hence, when assessing disbursement efficiency, we focus on management of the components of disbursements in isolation of the other inputs. To do this, we treat marketing and distribution expenses, operational costs, and management fees as non-discretionary inputs. Considering disbursements as non-discretionary is purely a methodological issue. The idea is to determine whether any improvement in the output is possible with the given levels of disbursements when the other inputs are unconstrained. This way, we are able to compute disbursement-specific output. This paper assumes each ion steel enterprise transforms the variable inputs of labor, energy, and iron ore, as well as the fixed input of asset, into the good output of crude steel production and two undesirable byproducts: industrial waste gas emissions and the industrial waste residue. The three variable inputs of L, E, and I are classified into two types: non-emission causing input labor and emission causing inputs energy and iron ore. The energy input generates an unintended output of industrial waste gas emissions and hence is an emission causing input. Similarly, material input of iron ore is an emission causing input because it creates an unintended output of industrial waste residues. The final picture is the one I have explained in this presentation. It should be noted that paper 1 and paper 2 utilize the standard weak disposability, but paper 4 and paper 5 shown in this slide use costly disposability to incorporate bad outputs. As can be inferred from my presentation, we can develop many different capacity utilization models to investigate various firms, industries, regions, and so forth. I think this framework has the great potential in various applied fields related to productive efficiency. Thank you for paying attention to my presentation.